So what if I have a vector x, so I have a function that takes from Rn to Rn. So I have a vector x, and this x is perhaps the response of the structure, and the force in the structure is another vector, but this is a non-linear, f is non-linear. And the non-linearity could be geometry, could be material, could be anything. But I have this relationship from every response to the structure. I have f of x, but f of x is non-linear, but f of x is a vector. So I have x1 and so on up to xn. And usually the problems are set up such that f of x corresponding to each degree of freedom x1 all the way up to xn, I have f1 force, normal force f1 up to fn. And what we say is that I have the force vector f, capital F1, and so on, up to capital Fn. And I want to find y that corresponds to the external force vector F. So I want to find a vector y that corresponds to an external force F. So I'm going to use a Taylor expansion. First, I would like to find F1. So first, assume an initial guess x naught, which has x naught 1, x naught 2, all the way up to x naught n. And then each component I'm going to utilize a Taylor expansion. The component f1 of x naught was delta x naught. f1 is a function of all the components of x. This is equal to f1 of x naught plus partial f1 by partial x1 delta x1 plus partial f1 by partial x2 delta x2 plus partial f1 by partial x3 delta x3. So this delta x01, delta x02, delta x03, and so on. f2 of x naught plus delta x naught. The second component of f is equal to f2 of x naught plus partial f2 partial x1 delta x naught 1 plus partial f2 partial x2 delta x naught 2 plus and so on. And so what you get is that the vector f which is equal to f1, f2, and so on is equal to the vector f of x naught. As you can see, f1 is equal to f1 plus a matrix that's made out of partial f and partial x multiplied by a vector of delta x naught, where the components of the vector are partial the component of f with respect to partial component of x. Plus other terms that we ignore. And if this is the capital vector f that we're looking for, then the vector delta x naught will be equal to f, the vector f minus the vector f of x naught, multiplied by partial f by partial x. This is a matrix, power -1, the inverse of that matrix. Compare delta x naught with x naught, and compare of f of x1, which is equal to x naught, with delta x naught. Compare, small f with f. However you want to compare them, you can compare them component by component. You can compare them using the Euclidean norm, norm f minus small f, norm f, norm delta x naught, compared to norm x, for example. By comparing the norms, because now we've got vectors, by comparing the Euclidean norm, I can know how close these two are. So how close this is to 0, and how close norm delta x naught is to 0 as well, because I want it as small as possible. And so based on how good, based on whatever criteria I put, that's when I know what if I achieved the good approximation that I'm looking for or not. Now, Mathematica does this for you using the using the command find root. So if you say find root and you put your equation, for example, as we will see, x cubed equal to 12, find x, and you have to put in x naught for, this is the initial guess. Yeah, because I'm using the find root is just the new application of the Newton-Raphson method. And the application of the Newton-Raphson method, I have to give it an initial guess. And so you just put here the initial guess, and the software finds it. So we have 3 problems. So I have f takes from R to R such that f of x is equal to x cubed. And I want to find a vector y such that f of y is equal to 12. Basically, what is the cubic root of 12? Another example, I want x such that 20 is equal to 20x power 4 plus 3x. Now both of these two are just linear, are just 1 degree, or f is from R to R, but there's nothing, you can do this for any dimensions. So f from R2 to R2, I have an example such that for every x, the function is a nonlinear function. The first component has this form, 20 x1 power 4 x2 plus 3x2 power 3. So I take the first component, power 4, multiplied by the second component, plus 3 second component cubed. That's the first component of the solution, and the second component of the solution is 20x2 cubed, x1 squared. And I want x1 and x2 that correspond to 20 and 1. And we're saying, in the problem, we're using 0.5 accuracy criteria for both. Comparing this with F, and comparing this with xk. Comparing this delta xk with xk, I just want to make sure that I'm within 0.5%. Comparing f of x plus delta x, comparing it with capital F, I just want to make sure that I'm within 0.5%. So these three problems, you can solve them using mathematics simply by just typing find root, the equations, and I posted all this on eClass already, so you're going to find it. But I just would like just to solve the second question, the last one, because that's the probably the slightly more complicated one. It just because it just has two components. So we are looking for f1 of x naught. So utilizing an initial guess, x naught equal to 4, 4. This is x naught 1. This is x naught 2. So f of x naught, or f of x naught plus delta x naught, I want it to be equal to 20 and 1. But it's not equal to 20 and 1. It's equal to f of x naught plus partial f by partial x naught, and this is a matrix multiplied by the vector delta x naught. So what is partial f by partial x naught? This is a matrix. Partial f1 by partial x1, partial f1 by partial x2, partial f2 by partial x1, partial f2 by partial x2. This is E, x1 cubed, x2. This is x1. This is f1, partial f1 by partial x1 is equal to this. Partial f1 by partial x2 is equal to 20 x1 power 4 plus 9 x2 squared. Partial f2 by partial x1 will be equal to 40 x2 cubed x1. Partial f2 by partial x2 will be equal to 60 x2 squared x1 squared. So this is this matrix, partial f by partial x, no, partial f by partial x. And so, delta x naught, which is the vector made out of delta x naught 1 and delta x naught 2, will be equal to, I'm just going to put here partial f by partial x, the matrix, -1, the inverse of that matrix, multiplied by the vector made out of 20 and 1. This is 20 minus f1 of x naught, and this is 1 minus f1 of x naught. Are you guys following? this will be equal to 20 x naught 1 over 4 x naught 2 plus 3 x naught 2 cubed, and this will be 1 minus x 20 x naught 2 cubed x naught 1 squared, where x naught 1 is equal to 4 and x naught 2 is equal to 4. That's x naught, the vector. The initial piece. And from here you calculate delta x naught. Delta x naught will be equal to negative 0.862 and negative 0.5689. So this is problem 1. I'm just going to show, and this is right. I was solving this one, and I just want to show you the table. When x naught 1 is 4 and x naught 2 is 4, this is it. The first component of the vector, the second component of the vector solution. Now the percent difference, f of xy minus f divided by f, the percent difference is actually huge. That's why I didn't even put it here. And then delta x1 and delta x2 are these. These turn out to be 20%. When you look at the normal of the vector, it's 20%. And so this is delta x1, delta x2. You calculate now, you put now x1 and x2, and now calculate f1 and f2. Still huge, I mean really far off. Calculate u's, u delta x1, u delta x2, and so on. You keep iterating until you achieve less than 0.5%. I think that's the criteria that I put in the increment in your delta vector, and less than 0.5% in the difference between f of xy and f. And so you can see here that I want this number to be 20. I started at 20672 because my initial guess was far off, and it moved down all the way up to 19.883. In fact, I put enough numbers, put enough accuracy that the computer displayed 20. And same with here, it went all the way down, 1.0096, but I put enough digits so that the computer actually showed me 1. And it took 11 iterations to achieve this accuracy. In the next problem, the purpose of this problem is to understand what the problems in structural mechanics look like. In structural mechanics, the problems are usually involved with a minimization of a function. So I have a function, this f of xy, it's a function of two variables. And this function could be of the displacement of your structure. You have n numbers, you have n displacements in your structure, n degrees of freedom. So you have a function, the energy of your structure is a function of those n degrees of freedom. So a function of n variables. And I want the n variables that would minimize the energy. This energy could be, so here, for example, I have f of xy. F of xy has this form, 1 plus x plus 5 squared, plus y minus 2 squared, plus 2x squared, y squared. And I want to find the minimizer of this function. I want to find the value of x, s, and ys such that this function is minimal. So I want to find this particular point. So here I just plotted the function, plot 3D the function between negative 50, 50, y from negative 50, 50, just so that you visualize this problem. Now, you can find the minimizer using Mathematica right away. There's a function called n minimize, numerical minimize, and you'll find the solution. The solution is equal to those two numbers. That's what minimizes this function. But for us to, what structural mechanics problems do is to minimize this function, we are calculating the derivatives. And the derivatives, so this is the energy. And the equilibrium equations are the first derivatives of this energy function. Partial F by partial X is usually sum of forces in the X direction, for example, is equal to 2x plus 5 plus 4xy squared. I want this, because we're saying that the function is minimum at this point, I want this to be equal to 0. And partial F by partial Y, which is equal to 2y minus 2 plus 4x squared y is equal to 0. So I'm looking for the solution to this problem that says I want partial f by partial x equals 0 and partial f by partial y is equal to 0. So I have two equations, but two nonlinear equations in two unknowns. The unknown xs and ys. So now I can utilize the Newton-Raphson method. So I can assume initial guess, an initial guess xs is equal to 4. For example, ys, x naught, let's call it x naught, and y naught. The initial guess I assumed here was 4 and 0. And what let's call this G1 of x and y. This is G2 of x and y. I'm going to call this a vector G. So G of x and y, or x plus G of delta of x naught plus delta x naught, y naught plus delta y naught. I want this to be equal to 0 and 0. I want this to be equal to 0. This is equal to G of x naught, G1 of x naught, y naught, and G2 of x naught, y naught, plus a matrix which is partial Gi by partial xg, where xg is x naught and y naught, is x or y, multiplied by delta x naught and delta y naught. And so delta x naught and delta y naught can be calculated. But why did I give you another problem? It seems to be the same as the previous problem. What is important to see in this problem is the fact that this matrix is symmetric. Now, why is this matrix symmetric? This matrix is symmetric because, let's look at partial Gi by partial. Let's look at partial G1 by partial x naught, and let's, by partial y naught, partial G by partial y, partial G1 by partial Y, and let's look at partial G2 by partial X. G1 was partial F by partial X. So this is partial F by partial X by partial Y, which is partial 2F by partial X by partial Y. G2 was partial F by partial Y, and I'm taking this with partial X, so this is partial 2F by partial X partial Y. So because of the existence of what we call the strain energy of the structure, so I'm just now talking analogous to, how is this analogous to structural mechanics? In structural mechanics, we assume that there exists a strain energy function, and the solution is the minimizer of that strain energy function. Because of the existence of that strain energy function, the matrix that relates our increments to, or from which we calculate our solution, is symmetric. And this matrix is what we call the Hessian matrix of the energy. This is partial 2F partial X squared. So this matrix is symmetric. So again, we just utilize that procedure and solve and find delta x naught and delta y naught and so on, and find a better approximation and so on. I think that you have to notice that this matrix is symmetric. So two additional problems. The two additional problems that are in the notes, just to see how this applies to any of the stuff that we're doing. So the first problem is just a problem with material nonlinearity. I have a material nonlinear problem where the stress is related to the small strain using a nonlinear equation. The stress is not directly proportional to the strain. The stress is equal to 10 multiplied by the uniaxial stress is equal to 10 multiplied by the uniaxial strain plus this number. Epsilon. It's a nonlinear relationship. So let's first look at the if I want to obtain the exact solution. We have, this is sigma, this is sigma plus partial sigma by partial x dx. And this is the distributed force negative x squared. And the equation of equilibrium is partial sigma by partial x minus x squared equaling 0, which partial sigma by partial x is equal to x squared. But sigma is equal to 10 du by dx plus 1000, or whatever, 1, 2, 3, 4, 5 du by dx cubed. So I'm going to put this here, d by dx squared. And get a non-linear differential equation. And the only way you can solve this differential equation is using in Mathematica, what is it called? The ND solve, non-linear differential equation solve, or numerical differential equation solve. So you're using a certain, I don't know what, I think they use Runge-Kute to solve non-linear differential equations, and you get the solution for the displacement and the solution for the stress of this form. Now, what if I would like to utilize the Newton-Raphson method, what we studied, the Rayleigh-Ritz method, to find a good approximation for this displacement and for the stress. The Rayleigh-Ritz method starts by assuming a displacement function for this rod. So we're going to assume, for example, so for the Rayleigh-Ritz method, we're going to assume that the displacement is equal to A0 plus A1x plus A2x squared. Implement essential boundary conditions. When you implement the displacement, implement essential boundary conditions, you get the displacement is equal to A2 x squared minus x. And that would ensure that the displacement u is 0 at the beginning of the rod, and u is 0 at the end of the rod, which I think has a length of 1. Yes, the length is equal to 1. The potential energy of the system is equal to the integral of the stress multiplied by the strain, multiplied by the integrator over the volume, actually, the potential energy is equal to the internal energy minus the work done by external forces. The internal energy is equal to the internal energy per unit volume integrated over the volume. The work done by the external forces equal to F, where F is equal to negative x squared, multiplied by integrated over the length. So this is equal to C. The volume is equal to the area multiplied by dx minus or plus u x squared dx. The strain energy, because it's not linear, is equal to the stress multiplied by the epsilon, and the stress is equal to then epsilon. Plus epsilon cubed d epsilon. So the strain energy that will give me this relationship between the stress and the strain looks like this: 5 epsilon squared plus this is the strain energy that I'm going to use, and epsilon is equal to du by dx, and so the potential energy will be equal to the integral of C area dx plus x squared u integrated over dx, and this is a function of the only variables that I have in the equation is A2. The only unknown after integration is A2. Use the Newton-Raphson method to find minimizer of potential. So now, partial potential energy by partial x is equal, for partial potential energy. So partial potential energy by partial A2 is equal to 0. This is a non-linear equation. To solve this nonlinear equation, I have to utilize the Newton-Raphson method and find the second derivative of partial potential energy with respect to A2, find the second derivative, and use the Newton-Raphson method. Now, if you use higher terms, for higher terms, the potential energy is function of A2, A3, and so forth. Use Newton-Raphson method to find minimizer of potential energy, because now we're going to have a set of equations. Partial potential energy by partial A2 equals 0. Partial potential energy by partial A3 is equal to 0. Partial potential energy by partial A4 equal to 0, and so on. To solve this set of nonlinear equations, I have to utilize the Newton-Raphson method. To utilize the Newton-Raphson method, I need to take derivatives again to find the matrix, and that matrix has to be symmetric because it will be the second derivative of the potential energy with respect to A2 and A3 and A4. It's going to be what we call the Hessian matrix of the potential energy. And you can see that the solution using 4 terms approximates, is getting closer to the numerical solution that Mathematica was obtained using another nonlinear, using a solver for the nonlinear solver for the differential equation. So this example shows you that an example of where the relationship between the stress and the strain is nonlinear, so I have to utilize the Newton-Raphson method to find a solution to the differential, to the equation of equilibrium, or to minimize the potential energy. Another example is if I have material nonlinearity. For this particular problem, I have 2 bars, 2 links, connected, and under a force F. Their bars are linear, so the relationship between the stress and the strain is a linear relationship. Using a unit cross-sectional area for each bar, we need to find the displacement at equilibrium of the following system. So it's a non-linear problem because it's geometric nonlinearity, because the final solution will depend on both the stiffness matrix is nonlinear, it depends on the solution. So to find this, to solve this problem, first we have to write the potential energy of the system. The potential energy of the system is function of, so I'm going to assume two bars that this point moved upwards U1 and moved horizontally U2. So this is where the new point is, and I'm trying to find U1 and U2 that would minimize the potential energy of the system. Find U1 and U2 that would minimize potential energy of the system. So what is the potential energy of the system? Potential energy is equal to the internal energy minus the work done by external forces. The internal energy is equal to the, for every bar, is equal to, so the stress is equal to, so the stress multiplied by the strain divided by 2 multiplied by the area multiplied by the length of bar 1 plus the stress multiplied by the strain divided by 2 multiplied by the area multiplied by the length of bar 2 minus the work done by the external forces is equal to F multiplied by U1 so the stress is equal to 10 strain, so this is equal to 10 the strain in the first bar multiplied by the length of the first bar divided by 2 plus 10 the strain in the second bar, and the area is equal to 1 multiplied by the length of the second bar divided by 2. F is equal to -1, so plus U1. So I'm looking for U1. Now what's epsilon 1? Epsilon 1 is equal to L1 minus L naught 1 divided by L naught 1. And L1, the length of the bar, this is L naught 1. This is U2. This is U1. So epsilon L1 is equal to the square root of L naught 1 plus U1 squared plus U2 squared plus U1 squared. The strain in the second bar is function of the length minus the length, and the length of the second bar after deformation is equal to L2 minus U2 plus U1 squared L02, the initial length minus U2 squared plus U1 squared. And so the potential energy is function of U1 and U2. A large equation containing the square roots of U1 and U2. And I would like to find U1 and U2 that would minimize the potential energy. So I would like to find U1 and U2 such that partial potential energy by partial U1 equals 0, partial potential energy by partial U2 equals 0. this is a set of two non-linear equations. To solve this set of two equations, non-linear equations, I have to utilize the Newton-Raphson method. So I have to take the derivatives again. When I take the derivatives again, I'm going to get another matrix that will will be symmetric, because I will have the second derivatives of that potential energy with respect to U1 and U2. So you can do it by hand, but one important note is the following. We started with the potential energy and obtained partial potential energy with respect to U1 equals 0 and partial potential energy with respect to U2 equals 0. But you could have started by saying the sum of forces in the horizontal direction equals 0 and the sum of forces in the vertical direction equal to 0. And the equations that you obtain will be exactly those two equations. This is equivalent to saying sum of forces in the x direction equals 0, and this is equivalent to the sum of forces in the y direction equals 0. Because the way we derive that potential energy function originally is by integrating the equilibrium equation. We came up with what we call the potential energy of the system by integrating the equilibrium equations. And we said, okay, well, the equilibrium equations minimize the potential energy of the system. So if I start with the potential energy of the system and differentiate it with respect to horizontal displacement and the vertical displacement, I obtain the equilibrium equations again. And so in your notes, I also started with, you can start by sum of f x equals 0, and sum of f y equals 0, and you get the same equations. Now they happen to be the same equations only because U1 and U2 happen to be the horizontal displacement and the vertical displacement. If you choose your unknowns to be different, let's say if you choose your unknowns to be this diagonal displacement and another displacement, or any other two unknowns, then the same solution would be obtained, but the equilibrium equations would not look like the equations that you obtain by minimizing the potential energy. So one small note before I give you a break. In everything that we did so far, we have to calculate the derivatives. And every time, let's look at the table above. It's not clear in the table, it's clear not in this table. Well, it's not clear in any table. So every time we come up with a new solution, or every time we come up with a new approximation, you have to calculate this matrix at the new, and then invert it. Then you find a new approximation, then you calculate this matrix, and then you invert it. Every time you find the new matrix, and then you invert it. So every time, when you look at the Newton-Raphson method, if this is the initial point, you're finding the slope, and then dividing this. When I say dividing, because we're calculating the inverse of the slope. We're using the inverse of the slope to find my new approximation. And then right here, I calculate a new slope, invert that slope to find this number. After I invert that slope and find this number, I have a better approximation, and so on. Now, this method converges really fast in terms of the number of iterations. But the problem that you encounter is that there's a lot of calculations. If you're using a software, there's a lot of calculations. There's better methods, for example, modified Newton-Raphson method. A modified Newton-Raphson method, you calculate the slope once, and you invert it once, and then after that, you just use the same slope. Now, this will utilize way more iterations, but it might be faster if calculating the stiffness or finding that stiffness matrix or inverting it takes a lot of numbers. You calculate the inverse once, and once you calculate the inverse, you just keep multiplying it with a new increment. And depending on the whatever software, this option could be there or not, but this is called the modified Newton-Raphson method. Now this is really not this is just the non-linear problems, solutions to non-linear problems. So it's not the purpose of the course to understand all these different methods, but they are available whenever you're using finite element analysis. Whenever you use a non-linear step, it tells there are options. Do you want to change the options? If so, in the future, if you want to change the options, you might want to change you want to use a modified Newton-Raphson method, the Newton-Raphson method itself, or something called the Secant method. In the Secant method, you actually have two initial guesses, and from those two initial guesses, you don't really calculate the slopes explicitly. You don't really calculate partial by partial. You calculate the slope implicitly by having f of u naught, f of u1 minus f of u naught divided by u1 by u naught. So you calculate the slopes. You approximate the slopes using differences. And so this is another method that's called the Secant method for for problems where it's not easy to calculate the derivatives. And so the first problem that we solved, or that I introduced, where I would like to find the cubic root of 12. I hope the table is above, maybe it is. Yes. So to find the cubic root of 12 using the Newton-Raphson method, using 4 iterations, I obtained this accuracy, 0.002%. If you and here, every time partial f by partial x is calculated and inverted, and new partial f by partial x is calculated and inverted. If you try it using the modified Newton-Raphson method, where you calculate the slope once and you never change it, then you see that you need so many iterations to achieve even worse approximation than we achieved using the Newton-Raphson method. Of course, depending on the software, if you're doing non-linear problem and you're using the modified Newton-Raphson method, every few iterations, the software recalculates partial f by partial x. Every few iterations, partial f by partial x is recalculated just to make this procedure faster. Now, implementation in finite element analysis, we're going to cover a lot of these things in finite element analysis. I think this should be R. How is this implemented in the finite element analysis? In the finite element analysis, I have a vector of external forces, which is what we call R, a vector of the external forces applied on the structure. And I have a vector calculated of what the external forces that correspond to the displacement is, because I have the relationship between the forces and the displacements. So given the displacement, I know what the external forces should look like, the vector of external forces. Comparing this with this, R with the internal forces, and so R minus the internal forces, this is a vector of what we call the residual forces in the structure, and And the final attempt analysis software makes sure that the residual forces is less than whatever number, maybe 0.005%, depending on whatever numbers they use. They make sure that this is less than a certain percentage of the residuals. And also, every time we're doing an iteration, that the increment in the displacement that we use is not too large. Because if it's too large, you might be vibrating around, maybe the structure is not in equilibrium. And so depending on your application, you might want to relax one or two. Depending on what application, you might want to relax one or two. I'll give you a very good example, just happened 2 weeks ago, where one of my students was trying to analyze a structure under no load. There was no load on the structure. And as the student was applying, it was just applying displacement on the structure. And as it's applying displacement, it's applying a very large displacement, but there's really no load, because it was just rotating a structure. But as it's rotating, what's happening is there was some numerical errors that introduced forces, fictitious forces in the structures, but they were very small. And so this error was huge. So 10 power negative 9, but 10 power negative 8 compared to 10 power negative 9 is huge. Because the software doesn't not look at it as 0. It's depending on whatever numerical, then the machine that you're using in so many things, if you're comparing 0 with 0, but they're not really 0, the software doesn't know what units you're using, whether this is Newton. It's all it does is compares the external forces, the residual forces, with the internal forces. So if I'm comparing 10 power negative 8 to 10 power negative 9, it's only 10%. So this is a huge error. So the software says that there's no, you have not achieved convergence, and the solution to this was just to apply a very small fictitious force that does not really change the structure, but it would just raise the vector of applied external loads to slightly above 0, just for practical purposes. So you really need to understand when you're doing some, I get every time somebody is doing some nonlinear problem, in Abacus I get an email from a student telling me, the software says too many attempts, I've done too many attempts and I've not reached a solution. What should I do? I can't give you an answer to this because every problem is different. This is one problem. You have to read the message. You have to understand the physics of the problem to know why you're not reaching, why the software is doing too many increments without achieving a solution. It could be as simple as there's no forces on the structure. It could be as simple as the structure is unstable, and so the displacement increment is huge compared to you have achieved force convergence, but every time as you're doing the Newton-Raphson method, the structure is being displayed a huge number of the delta U is huge, and so the software is saying I have not achieved, displacement convergence has not been achieved. So you really need to understand why you're not reaching why too many attempts were tried. Now, for Abacus, so Abacus convention, this is the response. This is the load step. I would like, for example, F, I would like the solution. So in a load step, you apply 20 or 200 Newton, for example. Usually, the full load step corresponds to a fictitious time if you have no if the structure response is not time dependent, so this is fictitious time. Let's say t is equal to 1 or whatever fictitious time you put. This is equivalent to 1 unit of time. Each, because this full load might leave the structure to a really deformed shape, it's better not to apply the load all at once, but we apply it in increments. When we apply it in increments, we first apply, let's say, 0.01 F, and so on. So these are called load increments. And the amount of increment is controlled by the time of increment. So this redundant variable time is just used, even if your structure is not time, it's not time dependent. This response is not time dependent. The variable time is just used to control how much, what's the percentage of the load that I should apply in each load increment. And to jump, to achieve a solution at a particular load increment, this procedure where I calculate the slope and I find in U, so this is my x0, and this is my x1, this is called an iteration. So there's a few iterations until you achieve one load increment. Each load increment takes a few iterations. And next week, I think I'll just spend it showing you all this within the Abacus, the environment of the Abacus software, where all these things are, where's the load increment, how do you put the load increment, what does the iterations mean, and all these things. All right, so we have just a small section left, how to apply constraints, so I'll give you 5 minutes. So we'll start again at 10:20 past 10.